Okay, first of all, I want to share with you the course content. We would be in the entire training, we would be covering both the core as well as the non-core components. So the entire training would be almost 60% of hands-on compared to the theory sessions which we would be having. So we would be dealing with the Hadoop core components and Hadoop architecture, MapReduce architecture. So we would be covering HDFS and MapReduce as the core components. Once we complete the course components, we would be moving to the Hadoop ecosystem components like Hive, Pig, Scoop, Oozie, Flume, and HBase. So I would be explaining all the components in detail, and we would be having separate hands-on sessions for each of these components. And for the entire training, I have a customized Cloudera Hadoop distribution which has all the exercises and all the training materials preloaded. So once we install that on your system, so whatever hands-on we are having, so you would be directly following the hands-on material with the software provided. So today let's go ahead and discuss the introduction of Hadoop. So before even starting off with discussing Hadoop, first of all, what we need to understand is that why does Hadoop is required. So basically we would be discussing what were the problems with the existing traditional large-scale computing systems, what requirements an alternative approach should have had, and how Hadoop addresses those requirements. So basically prior to Hadoop coming into picture, in fact there were traditional large-scale computation systems which used to process data, or which used to handle data in the same way like Hadoop does. But there were some of the drawbacks and disadvantage of the traditional large-scale computing systems, which made people to think of an alternative approach, and that's how Hadoop came into picture. So basically we'll start discussing what were the reasons. So the first thing is that the traditional large-scale distributed systems were mostly processor bound. So people used to think that let's increase the processing power, or let's increase the processor configuration, and we will get a better performance. Like they used to increase the processor power, they used to increase the RAM, but that it doesn't used to solve the problem. So basically the problem was that a single machine, even though you increase the hardware of that particular machine, still it won't be in a position to handle data or to process data after a certain point of time. So that particular thing caused distributed systems to evolve. So when I say distributed systems, that means you have multiple machines in parallel which are doing work. So basically you have a data which is pushed to all the machines in parallelly, and your processing happens simultaneously on all those machines. So that is what is a distributed machine. So basically for a particular single job, we used to have multiple machines which used to process the entire job effectively. So these are some of the MPI, PVM, and Condor. These are some of the older distributed systems. Moving on to the next slide. So in the previous slide we talked about the traditional large-scale computation systems, and we also spoke about the distributed systems. So now when people started using the distributed systems, they started even facing problems with that. So let's discuss what the problems were. So first of all, the programming of the distributed systems was not very simple. It's really complex. So the reason why it is complex is because you have multiple machines in parallel which are doing a processing of your data. So you need to have a synchronization between each of these machines. Synchronization meaning that a particular data is being processed by one machine and a particular part of data is processed by another machine. So you need to link the overall consolidated result or the overall consolidated data, right? So that is what is called as synchronization. So basically what the problem was that you used to have a finite bandwidth. I mean the network bandwidth used to be very limited. So this entire synchronization used to take a lot of network bandwidth, because of which at most of the times the synchronization didn't used to happen properly, which used to cause the results to fail, or you would get results which were not correct. So that was the one of the problem with the traditional distributed systems. Also, one very important thing is that which we call as a partial failure. So basically, when you have multiple machines working in parallel and one machine goes down, so whatever the job or whatever the work that particular machine was doing, so it gets halted, meaning there is a break in the entire execution and the overall execution couldn't get complete because one machine which was doing a particular X amount of work that went down, and there is no one to take up that work, or no one is there to delegate that work which the machine went down was doing. So dealing with partial failures was a very crucial thing for distributed systems, and there was no such mechanism in the older time wherein the partial failures could be handled for the distributed systems. So let's move on and see few more problems with distributed systems. Second thing is data storage. So basically, for the distributed systems, the data used to be stored on a separate physical network device, network drive, which is called SAN. So what used to happen is that when we are running our processing or when we are running our job, so from the network storage, the data used to get copied to the individual machines. So when I say compute nodes, so compute nodes means individual machines. So data used to get copied on the individual machines, and then the processing used to happen. So it's like you're copying data from one place, putting into a machine, and then you're running your job. So what is happening over here is that the time which it takes to copy data from a network, from a network storage to the individual machine, that used to be huge for larger files. So that's why this particular thing works fine only when you have a limited amount of data. But when the data grows, right, suppose this will work fine when you have, say, data in terms of megabytes or let's say gigabytes, but when you start moving ahead, when you go ahead with terabytes, petabytes, and in more than that, so this particular thing will fail as in copying a 1 terabyte file to individual machines from a network storage itself will take a lot of time, and after the data gets copied, then only you can run your processing. So this is the second important aspect of the distributed systems, which was data storage. So the same thing which I was trying to explain in the previous slide. So the older distributed systems will be fine as long as the data size is not huge. So since we see the examples over here that Facebook is handling over 70 petabytes of data, eBay is having over 5 petabytes of data. In fact, this particular figure which you're seeing, this in fact is like a couple of months old. So in fact now there would be even more than this. So you see that nowadays all organizations or all institutions, they are generating data at rate of terabytes per day. So the existing distributed systems, they are not competent to handle or process the terabytes or even more than terabytes amount of data. So in the previous slide, as I was trying to explain that in the older distributed system, you used to copy data to the individual machines and then you used to process. So let's say that for a particular machine, for a particular drive, hard drive, you have 75 megabytes per second as the disk transfer rate. This is kind of a fastest disk transfer rate. So suppose you have a 100 GB file, right? So a 100 GB file would take 22 minutes approximately, to copy from a shared network storage. So in fact, this 22 minutes is also fine when you have sustained reads. Okay. In fact, in real time scenario, due to network bandwidth or due to system hardware, in fact this particular time will be even more, right? So that's what, when you are trying to copy data from one external system to one system and then you are running your processing, so you are ending up spending most of your time in just copying the data rather than concentrating on the processing. So definitely the logic which was putting in the existing distributed systems, this will never hold good when you have data of huge volume. That's why a definite new approach was needed. Moving on to the next slide. So partial failure. So initially we discussed about traditional large scale computing systems, and then we moved into distributed systems. So partial failure is one of a very important aspect when we are actually working with multiple systems. So when one system or one component goes down, so the overall execution shouldn't get affected. So it's not like when I'm processing huge amount of data and one machine goes down, so other machines are waiting for this machine to be rectified. So this involves a lot of wastage of time and resources. So the existing distributed systems, they were again not capable to handle partial failure. So definitely a new approach was required, wherein if a particular system or a particular machine goes down, then the overall execution has no effect. That is what is called as a partial failure support. Okay, moving on to the next slide. Yeah, data recoverability. So this is associated with the partial failure. So suppose a particular system fails, right, and it was doing some amount of work at that particular time. So the entire failure which happened, it shouldn't result any loss of data, because the time when that machine comes up, so it should be in the exactly same state which it was before going down, so that there is no loss of data, because data integrity, data sanity is a very important aspect when we talk about big data technology. So this aspect was also missing in the existing distributed systems. Next is component recovery. So so when the particular system which went down, it comes up, so it should have the capability to join the other group of systems. As we are talking here about the the distributed systems, so if one machine goes down and suddenly it comes up, as in let's suppose it reboots immediately, right, due to some reason, so it should be capable to come back and join the other systems. It should be ready to use, which was missing in the existing distributed systems. So this is again very important aspect when we talk about distributed computing. So next up is consistency. So basically, for a particular job which is running at a particular amount of time, so individual component failures, it shouldn't affect the overall execution of the job. So there has to be some mechanism wherein a particular execution, even though it fails for some or the other reason, there has to be resources available which should take up immediately the work which this system was doing, and the overall job should get completed. So it shouldn't have an effect on the existing running process. That is what is consistency, which was missing in the existing systems. Next point is scalability. So scalability is a very important factor when we talk about big data or Hadoop technology, because here we are not dealing with data in terms of megabytes or gigabytes. Here we are talking data in terms of terabytes, petabytes, zettabytes, and even more than. So suppose hello.